Today we want to solve triangles. Not these kind of triangles, right? You know, I think impossible triangles. These are kind of fun that you can do them. But we'll actually run into impossible cases in our endeavors today. Just not that kind. But the topic today is solving right triangles. Extremely important topic. I'm going to make sure I give you one of these on the midterm and also on the final. When you get out of here, one of the things you have to be able to do is solve these right triangles, because these come up in all sorts of applications in construction and certainly in mathematics and crystallography and all sorts of other places in geometry in particular. And here's what we're going to do. We're going to use the trigonometric functions that we've defined in the unit circle to solve right triangles. So we'll say, first, we introduce this notation to be able to make our discussion more convenient. If I draw any right triangle, what I want to do is always call the hypotenuse C, we've already said. And the other sides are A and B, little a and B. So the sides ABC have the following construction. We'll put angle alpha opposite A. Angle beta will go opposite B. And then C, the hypotenuse, the longest side. You can give me an impossible triangle already by making C less than A or B, right? The hypotenuse always has to be the longest side. So when I give you some of these triangles and give you the specification, if the hypotenuse is not the longest side, then right, it's an impossible one. And what we're going to do for these is say each of these can be solved using one of our trig functions. We're going to write a trig function that relates two given numbers. I should have said each one of these can be solved given either two sides or a side at an angle. The idea is two independent pieces of information. I won't be able to solve it given two angles, right? Because they're not independent. Once you know one of these angles, the other one is complementary, 90 minus that. So it's really only giving me one piece of information. So if you give me the two angles, I could have it be this triangle or this one or this one. There's an infinite number of similar triangles and it's not solvable, right? But given two sides or given a side and an angle, this is my symbol for and. A unique triangle, a unique right triangle is determined, this together with the right angle. And so we'll go ahead and solving means find all the other sides and angles. There will be three that we don't know, right? We're given two pieces of information, plus we know there's a right angle. There's three things left to find in all these. So I'll give you 1, 2, 3 steps. The first one is the trig function relates the two knowns that you're given, right? And one unknown. Allows you to solve for that unknown side or angle. All right. Then the complementary angle theorem will let you find the remaining angle. All right. In any right triangle, these two angles add up to 90 degrees. So the three add up to 180. So if you know one, the other one's just 90 minus the first one. Complementary angles theorem for a right triangle. And then finally, the Pythagorean theorem, once I have two sides, gives me the third side. And we'll use the Pythagorean theorem solve for the third side to save a step. So that's what you do, is basically use trig function so that you now, instead of having two pieces of information, all but one angle, all but one side, the complementary angle gives you the last angle, Pythagorean theorem gives you the last side. You can actually use the trig functions to solve all three of these, but we don't tend to do that because it's usually easier to use these two. So you see all books do these three things, even though you can use a trig function 3 times to solve a right triangle. The reason is, the basis for trigonometry, that we have this unit circle, and oops. If you take a right triangle, it can fit into the first quadrant of it, right? 90 degrees is here, so these add up to 90. That makes each of these an acute angle, an angle of measure less than 90 degrees. And so it goes in the first quadrant. So whatever right triangle you give me, I fit it in the first quadrant. Maybe it looks like this, right? And because it's a unit circle, this side is 1, right? And now I can call this side, let's call this one A hat, and call this one B hat. And we noticed from the construction here that A hat, being the y coordinate, is the sine of this angle. I'll let alpha, since it's opposite A hat. And what we noticed from our trig relationships, that sine alpha is A hat over 1. But now if you give me any other right triangle whatsoever that has the same angle, maybe it looks like this. If it's got that same angle there and is a right triangle, well, then these two angles are in common, they're equal. They both have a right angle. So the last angle to add up to 180 degrees also has to be equal. If angles are all congruent or all equal measure. And so they're similar triangles. So any right triangle with the same angle here is similar to the one that goes in the unit circle, right? This is the basis for using trigonometry here. Now, if on the big triangle, I say this side length is B, and this is A, and this long one here is C, we notice the sine of alpha is this over this by our definition of the unit circle. The sine alpha using the unit circle is also equal to this side over this side by similar, this side over this side by similar triangles, right? This is to this as this is to this by similar triangles. It's equal to A over C. Similarly, the cosine of alpha is B hat over 1 in the little triangle has to be this one over this one, B over C in this one. And the tangent of alpha, well, that's A hat over B hat, has to be A over B. And so I can scratch these out in the middle. This is part of the proof. I'm just showing you that by similar triangles, these are equal. And then similarly, the cotangent is the reciprocal then of the tangent is B over A. The secant is the reciprocal of the sine is C over A. And the cosecant is the reciprocal, secant is reciprocal of the cosine, C over B, sorry about that. Cosecant is reciprocal of sine is C over A. And we notice that we can rewrite these all as ratios. So we'll say bisimilar triangles, these all hold. All right. And I'll just write this one again as A over C. I'll leave out the proof in the middle here. Let's see, this one was B over C. And so we could write it that way. Unfortunately, these letters get confusing to remember. It's really easier to think of in any right triangle. Sine of alpha, this angle, is equal to the length of its opposite leg, right? Leg, hypotenuse is opposite the right angle. It must be the leg over the hypotenuse. So we'll call that the opposite leg is OPP, or opposite, over the length of the hypotenuse, H by P. So on these, and when I write this here, I guess I better get rid of this. When I write OPP, that means length of the opposite side. When I write ADJ, that means the adjacent side length. And when I write HYP, that'll mean the hypotenuse length. Right? In all of these. So I can also write this as opposite over hypotenuse. And similarly, B over C. See, B over C is the length of the adjacent leg divided by the length of the hypotenuse. So I'll put adjacent over hypotenuse. This is really to be preferred because what happens is if you turn this triangle around and put alpha up here, now you've got to put A down here and B up here for these letters to work. And it gets very confusing to reorient yourself when the triangle is turned around at different angles. So it's easier to put opposite over hypotenuse, adjacent over hypotenuse. A over B would be opposite over adjacent. It's the tangent, etc. Let me compile them rather than try and squeeze it in the corner because these are very important. And I can leave out the intermediate proof step there. We'll say that is in any right triangle whatsoever by making it similar to the right triangle that fits in the first quadrant of the unit circle. The sine of alpha is opposite over hypotenuse. The cosine of alpha is the adjacent side length over the length of a hypotenuse. The tangent of the angle alpha, rather than memorizing the letter again, will be opposite over adjacent. The cotangent is the reciprocal of tangent is adjacent over opposite. The secant will be the reciprocal of the cosine as hypotenuse over adjacent. And the cosecant will be the reciprocal of sine as hypotenuse over opposite. So you need absolutely to memorize these now to solve triangles, because what you can now do is use these the three steps together with these definitions or results in terms of the right triangle to solve any right triangle given two sides or an angle in a side. And that comes up in lots of situations. Right. Let me look at an example. Suppose that I'm given a right triangle like this. Suppose I'm given that this is 42 degrees and this is 12 units long. Right? And it's a right triangle. Suppose I said solve the triangle. That means find all the angles and sides. And it's always three steps. Since you're given three things, the right angle and these two numbers, you have, and there's three angles and three sides, there's three more things to find, just those three steps. So the first step you can do, you don't have to do this one first. There is a little bit of variability in your choice. You can immediately find this angle by complementary angles. But just to be step by step, I'll always start off with the trig step. It doesn't matter. So I'll do the trig step, just those three that I wrote down before. I write a trig relation, one of these three, relating to two numbers I know and one that I don't. So I fill in the rest of these. If I were to call this alpha, then this one has to be A, right? Opposite, A goes opposite alpha. And then this one's beta is the remaining acute angle, so this has to be B, and then this has to be C. I need to find beta, C, and B, right? So the trig step is to relate any one of those unknowns I have by a trig relation. to the two numbers I do have? Well, I could say, let's see, the tangent is the length of the opposite side of the angle over the length of the adjacent. Now, see why it's important. I memorized it this way instead of memorizing the letters. I think it's better anyway, because I've turned the triangle around the backwards direction from the way I had it before, and so you've got to be able to flip it around in your head that way. Let's just do it this way. The tangent of 42 degrees is equal to its opposite side, 12, over the length of its adjacent side, b. And now I can just apply algebra with this. I'll say equivalently, this is by multiplying by b times tangent 42 degrees. And there's different ways to solve this with algebra, right? You can also take reciprocals and then multiply by 12, right? So we'll say b tangent 42 is 12 by multiplying both sides by b. And now I can divide by tangent 12 and I get b equals 12 over tangent 42 degrees. That's an exact number, but really what you want out in the field, my wife's father is a surveyor. What he needs to find out is how many feet is it, right? Not it's 12 over tangent 42 degrees feet. Your calculator can do all these things. What happened in the old days, right? Actually up through about the 1970s was people had these big books of trigonometric values. And what the book did was people figured out for each angle, what's the ratio of this side to this side, what's the ratio of this side to this side, so they could fill out all those trig functions and have a big book full of all these decimal places for what's the ratio of one side to another for each given angle from 0 to 90 degrees, between 0 and 90 degrees. And you could look that up. And once you knew that, you'd know the tangent of 42 degrees out of your book and you could figure B. And guess what happened to those books? Once in a while you see one in an old used bookstore. Don't buy it unless you want an antique, because it doesn't do you any good, right? Your calculator now does that. It essentially has a whole table in there, but you just push the buttons and it figures it out what would have been in the table anyway. And so you don't need a giant book from the bookstore anymore. But that's what people used to have to do before hand calculators came along in numbers in the 70s. And so B is 12 over tangent 42. I can figure it on my calculator. And here's how you do it. You have to make your calculator degrees mode, since I'm using degrees here. If you put it in the wrong mode, then you'll get the wrong answer, right? It'll treat, if you have it in radians mode, it'll take tangent of 42 radians. So degrees mode, here's how you get it. It depends on the calculator, unfortunately, but most calculators have a key that says mode. All right, and on the TI-84, a lot of you get this from high school. TI-83 is completely equivalent for practical purposes anyway. This is the same. After that, it'll show in here all sorts of things you can reset. Well, one of them is you can reset between degrees and radians mode. And so what you do is go through, select degrees mode. All right. Instead of radians, if it's in radians. If it's already in degrees, you can just leave it. And then when you're all done, you push second mode. And up above mode, it says quit. The second button up in the corner on this one is blue. They have different designer colors on these things. But when I push the blue button, it enables the blue instructions above the key. So this is blue up here. I push second, and this button, it says quit, get out of the mode setting. And it will switch it over 2 degrees if it wasn't in degrees already. Right? So that's what you can do on the TI-84. If you bought one of the more expensive TI-89s, then I think you have to push enter to exit instead of second quit. So it depends. You may just quit without changing them. This is on the TI-84. On some of them, you may have to use quit instead, or enter. On the TI-89, I think that's what it does. And other calculators are different, unfortunately. You just have to figure out from the instructions manual. Just try it a few times, you figure it out, right? So you get in degrees mode, and then to calculate this thing, you push 1, 2 for 12, right, divided by, and there's a button that says TAN. There's 3 trig functions on there: sine, SIN, cosine, COS, and tangent, TAN, and you can do any one of those 3. It doesn't have the last 3 on there. Can you guess why? Probably. Why wouldn't it have secant, cosecant, cotangent on your keyboard?
That's the inverse of the first.
Yeah, exactly. It's just, it takes up 3 more buttons on your front of your page here, and all you have to do is take one over one of these to get the other one. So they expect that you know the reciprocal relationships, and you just take one over tangent to get cotangent, for instance. So what you usually do when you're solving this, you don't use secant, cosecant, or cotangent to solve these, although you can. You usually use sine, cosine, or tangent because they're on your calculator with only one button instead of 3, right? Instead of doing 1 over. So I'll take 12 divided by tangent rather than 12 times cotangent, because cotangent isn't on the keyboard. Well, 12 divided by tangent, it will automatically insert a parenthesis on this thing. And on a lot of calculators, the new ones, it usually inserts 2. Then I'll put 42, and enter to evaluate it. If your calculator puts in 2 parentheses, well and good. If you have a TI-84, it will automatically close the parenthesis here, so you don't need to put a parenthesis. But if you bought the expensive calculator, TI-89 or the Inspire maybe, you have to close the parenthesis or throw an error. It expects you always to balance your parentheses. It's just a requirement. So on some of the calculators, if it puts 1 parenthesis on the left, you have to put this closing one, or it will throw a fit. In a sense, it's not bad to always close it, because sometimes people accidentally push this button twice somewhere and don't have unbalanced parentheses. They don't realize it and they get the wrong answer. They don't know it's because they didn't match their parentheses. So some ways it's good the calculator checks you, but some calculators you need to close this. Some calculators already insert 2, and some of them you don't need to close it. We'll close it automatically. All right, but here's the keystrokes at least, and maybe you need a closing parenthesis here. And what do I get on here if I'm in degrees mode? I've already put this in degrees mode. 12 divided by tangent 42 gives me 13. Let's put it over here, I guess. 13.3273, blah, blah, blah. Now, on a lot of these problems, it says round to so many decimal places. Suppose I said round this one to 2 decimal places. What does that mean? It means take 2 digits right at the decimal point. That's the decimal point. And so I round it right here. And then what happens if this is greater than or equal to 5, and it is, then you round this last one up and you say this is approximately 13.33. But if this is 4 or less, then you leave it at 2. That's the rule for rounding, right? So we'll say this is about 13.33 is the length of side B. All right, there's the trig step. We write a trig relation relating the 2 numbers we're given and one that we don't know, and we can figure out the one we know using the calculator, right? Here's the 2 decimal places, or 2 digits right at the decimal point. You don't have to write squiggly equals. I just do that to emphasize that I'm approximating this number, but you can just write equals. Now, the second step is very easy, right? We can have one angle where you can use the complementary angle theorem. Complementary angle theorem says that the last one is 90 minus the first one. So it's the first one given was 42 degrees. So I'll say the last one, beta, is 90 degrees minus 42 degrees. Gives me 48 degrees. And if I'm going to round it to 2 decimal places, I can call it 48.00. If this is an exact number, 42 degrees, you can just write 48 and tell people it's exact. But if this is a rounded number, then you put 48.00 degrees here. So this one's rounded to 2 decimal places. So you can put this. I'll probably accept 48 anyway. But if these are rounded numbers, then this should say 42.00 and this should say 48.00. All right, so that's the complementary angle theorem to get the last angle. Isn't this easier than doing another trig step? You could do another trig step, but why not? Why do that when you just subtract, right? So then the last step, it's usually easier to apply the Pythagorean theorem. Once you have 2 sides, you can find the third one. Well, we do, right? We started with A given, and now we have B. What's C, right? You can write the Pythagorean theorem, but we said it would be easier to use the Pythagorean theorem to solve for C. C is the square root of A squared plus B squared. Oh boy, let's write them in. I guess I'll put it in. All right, this was the Pythagorean theorem solved for the hypotenuse as the root sum square of the 2 legs. And let's put it up here. Hate to do this, but this is the square root of, let's see, a was 12 squared, 12, that's squared, plus we've got 13.33 squared, and we'll get some approximate number. I'll tell you what's faster on your calculator than doing this, probably, is you can do this. For a second, and how do you get the square root button on most calculator, on this calculator at least? Up above the x squared button is its inverse button, right? The square root undoes the square. So they'll put the square root on top of the square button. When you push second, the blue button on this calculator will enable this blue instruction above the square root. So I can take square root like that, second x squared, and then I'll put 12 squared. I already know that. That's 144 is the square root of 12. So I just, rather than put 12 squared, I'll put 144. Plus, instead of putting 13.33 squared, I always fat figure these things, right? Because the keys are real tiny and close together. Here's something you can do if you want. You can put 13.33 squared, but why not do this when you have lots of decimals in here? Actually, it's even important. Push second and the little minus key down in the lower right for negative numbers on the TI-84 at least. Some calculators is a different key. Second answer enables the blue ands button above, and this brings up the answer that was on the screen last. You're 13.33, right? And now what appears on the screen is this square root parenthesis, it automatically inserts, and then 144 plus, and second answer, it will say, it will put answer on here. And then I need to square it. So I'll push the x squared button, and it will put a square up here. And then I can just push enter because this one automatically closes the parentheses for me. So if I push enter, then this appears on the screen. It's taking the square root of 144 plus what was on the screen last squared. And what do I get? Try this one. Square root 144 plus answer squared. And I got 17.9337, etc. Again, if I'm going to round to 2 decimal places, then I'll say this is right. I count 2 decimal places right at the decimal point, and say this is less than 5, so I'll just leave it the way it is. It's 17.93 is the rounded approximation. Most of these digits will come off, and you'll get just rounded numbers all the time. There's an example. Solve the triangle, right? Use a trig relation to relate the 2 numbers you know and one you don't. Use the complementary angles theorem to find left angle. Use the Pythagorean theorem to find the left side. Easy, right? But you just have those 6 trig relations that give you the ratios for the 2 sides of any right triangle that you can use this to get that first key step, right? All right, so there's one of them. I'm sorry I had to kind of write around it a little bit to keep this up. So memorize these. That's what the star means. Let's try another one here. Some of these I'll ask you to solve exactly. It'll only be when you get a special angle. So if the triangle is a special triangle, a 30, 60, 90, or a 45, 45, 90, we can solve exactly. And a lot of these calculators now will actually do the exact solution too. Some of them will just do decimal. Depends on the calculator you bought. We can solve exactly in terms of roots instead of rounded decimals. And here's an example here. Suppose I'm given this one. This is 45 degrees here, and I'm given an angle there, and this side is 13 square root 3. This is off the homework page here. Suppose I said solve this triangle, find all the remaining sides and angles if this is a right angle. Right? So I'm given an angle on the side. I know I can solve this, 2 pieces of independent information. What can I do? I can first write a trig relationship, right? I can say, well, maybe I want to find this side this time, right? I could say the cosine relates the adjacent to the hypotenuse, right? So I find a trig relationship that relates these two numbers and one I want to find, like B. It doesn't matter which one. And if this is B, then this is A, and the opposite B would be beta. So here's the three things I need to find, A, B, and beta. So I'll write that the cosine of 45 degrees, according to this, is adjacent to the hypotenuse. So it's B over 13 square root 3, right? There it is. Well, evidently then, by multiplying by 13 square root 3, I get that B is 13 square root 3 times cosine 45 degrees. Now I can do it by decimal like I did last time with the calculator, but since this is a special angle, I know the cosine of 45 degrees exactly. What is it? All right. Well, I can run to the unit circle, or I can just draw the special triangle. It doesn't matter. And I say at 45 degrees, I memorize the triangle. It fits right in, right? It's square root 2 over 2, square root 2 over 2 and 1. And the cosine is the x-coordinate is square root 2 over 2. So this is 13 square root 3 times square root 2 over 2 from the unit circle equals B. And now I just need to simplify this. This looks like 13 square root 6 over 2. G is exactly 13 square root 6. Square root 2 times square root 3 makes square root 6 over 2. And I leave it like that in terms of radicals, because remember, the square root of any whole number is either a whole number, and square root 6 is not, or it's a non-repeating decimal. It goes on forever without a repeating pattern. So anywhere you round it is approximation. So I'll say there, by trigonometry, we get one additional side. Now we can use the complementary angles theorem and the Pythagorean theorem to finish it, or I can spend more time working more trig if I want. So this is step 1. I find this additional side. And then step 2, I can say, well, I've given one angle, I know the other one, right? Beta is the complement of the angle I have, 45 degrees is also 45 degrees. I already knew that, looked at it and saw it. And then step 3, I have everything beside A, right? I need to find A. So the Pythagorean theorem applies. Now A, recall, is the square root of c squared minus b squared, right? When you're solving for the hypotenuse, it's the root sum square, but solving for the leg, it's the square root of the difference of the square. So I'll say this is square root of 13 square root 3 squared minus b squared was 13 square root 6 over 2 squared. And if you have one of those fancy calculators, it will do this exactly. That's the advantage. It will do all this stuff exactly and maybe save you making a mistake on the test. The disadvantage is they have a longer learning curve, right? So you have to take more to figure it out. But if you're a math or science major, that's well worth it in the long run, right? All right. So now this is square root, 13 square root 3 squared is 13 squared, 169. Times square root 3 is 3, squared is 3. Minus, well, let's see, this is 169 times 6 over 4. And I can figure this all out if I multiply this top and bottom by, well, let's write it this way. 169 times 3 minus canceling the 169 times 3 over 2, right? So it's half of 69 times 3, taken away from 16 and 169 times 3. Gives us square root of 169 times 3 over 2. You don't want to leave it like that, right? Because 169 is a square. This is square root of 3 halves times 169. So you can leave it like that as far as I'm concerned, but if you want to rationalize the denominator, then it would be multiply top and bottom by square root. That's right, 169. Square root of 3 over 2, actually, put that last. I'll multiply top and bottom by square root 2 and call it twice this number, 338. Square root 3 over 2. this is the rationalized version. Either way is just fine. Right? Didn't write this right. It's not 169 square root of 169. It's 13. Apologies. 13 square root of 3 over 2. Or 13. 13 square root of square root of 3 halves, or 13 square root of 3 over 2. And then you realize when you're all done with one of these special triangles, duh, right? If this side, remember that in one of these, in these 45, 45, 90 triangles, this side is always supposed to be square root 2 times the other side. Remember this version of it, 1, 1, square root 2. So this is just square root 2 times as long as these sides. All you have to do to get these sides is divide by square root 2. That's what I've got here, right? 13 square root of 3 over 2. So apparently it checks. So on these special ones, yes, you can go through the long trigonometry steps and the Pythagorean theorem, but it's easier just to say, right, it's easier in this ratio than divide this by square root 2 to get the other two sides. Anyway, so, and maybe I should, same thing on this one. This one was 13. This should be 13. Do this right. What did I do? Oh, this was, oh boy. It should be square root 2. This should be the same one as that one. This should be 13 square root 6 over 2. Not sure what I did here. Square root 160. So this should be. Yeah, this is yeah, this is just square root 3 over 2. Sorry about that. 13 times square root 3 over 2, and this is 13 square root 6 over 2. But I'm multiplying top and bottom by square root 2. There we go. Okay, so I'm just tossed it right here at the All right, so there's doing one exactly. When you do one exactly, it can sometimes be easier just to use similar triangles, but we want to be able to do those because I'm not liable to give you the exact one on the test. All right, so that's given an angle and a side. What if I'm given two sides? For instance, this is one of my favorite ones to do. You've all seen this triangle before. Suppose this is side length 3 here and side length 4 here in a right triangle. I say solve this right triangle. All right? Find all the remaining angles and sides. So I've just got to label them somehow. If I call this one alpha, then this one's A. If I call this one beta, then this one's B. And this must be C. I've got to find alpha, beta, and C, right? So I'll go my trigonometry step and say, well, I'm given these two numbers and I can relate those to one of these other numbers. Let's say tangent of alpha, this one is this side over this side relates to two numbers that I know is 3 to 4, right? Opposite, again, opposite over adjacent, this one over this one. Now what's alpha? Well, here's the other thing the calculator does for you. It computes what we call inverse trig functions. For acute angles only, this won't always be the case when you're trying to find an obtuse angle. The calculator can find the angle that has a given tangent. As an inverse tangent, or arctangent it's also called. To find the angle that has a given trig function value. At least for the sine, cosine, and tangent. The other three you have to figure. Well, in this case, tangent, for the given tangent. But it'll also apply to sine and cosine. So I can use my calculator then to figure if tangent alpha is 3/4, alpha is the inverse tangent of 3/4, or arc tangent of 3/4. So some books they'll also write ARC TAN 3/4. I can do this on my calculator, right? All I have to do is in degrees mode again. I'm going to take second tangent, because up above the tangent key is its inverse, just like square root above is above square. Inverse tangent is above tangent. And so this will bring the inverse tangent function up. This is in blue above, the key here is blue, and this is in blue above the tangent. Some of them will have multicolors and multiple buttons you can push to get all the different functions above the keys. You can get quite a bit of functions on the keyboard that way. So second tangent, and then 3/4, I can put 3 divided by 4, or I can put 0.75, it doesn't matter. If you bought one of those expensive calculators, I recommend pushing 3 divided by 4. And this will automatically insert a parenthesis here, by the way, and some calculators will enter 2. And if you're not required to close this parenthesis, then you can push enter here. All right, so on the screen on the TI-84, this will say arc tangent. These two buttons make this one thing appear with a parenthesis, automatically inserted. Then it'll take 3/4. Slash is the computer programming symbol for divide. So it means when you push this button, this appears. And then if you don't bother to close the parenthesis, you don't have a more modern calculator, it automatically does it. Then this will appear on the screen. Some calculators, the closing parenthesis appears. This is on the screen. These are the keys you push. And let's see what it gives us in degrees mode. What if it's not in degrees mode? Does it give you the radians measure, right? So let's try it in degrees mode and see what we get on the calculator, because I left it in degrees mode. Second tangent, 3 divided by 4. And I said, on the fancy calculators, you want to do this because it will give you an exact answer. If you put numbers with no decimal points on here, it will give you the exact answer. Once you do this, if instead of this you put 0.75, it will assume this is a rounded number and it will give you a decimal. So that you'll lose your advanced calculator advantage if you put a decimal point in there. In fact, when I want a decimal, say I want the arc tangent of 1, and there's no decimal, I'll just put 1 point in here. That way it will give me the decimal answer instead of the exact answer. So if you want an exact a decimal answer, don't put 3 divided by 4, put 3 divided by 4 point, or 3 point divided by 4. Any decimal place will tell the calculator that's a rounded number and it will round everything. But if it's in the mode where it will do exact answers, you want to put 3 divided by 4 here and get an exact answer, if you can. This one, unfortunately, however, doesn't have an exact answer, so it'll give you a decimal anyway. What it does is, if it's in what they call best mode, then it will give you the exact answer if it can, and if it can't, it'll give you the decimal. So, or it will just leave it. In fact, this is one of the most frustrating things on the TI-89 when you buy it. This is why it has a slow learning curve. If you put arc tangent 3/4 on there, it will leave it. It will show this on the screen. Arc tangent 3 divided by 4. What? I mean, that's what it'll appear. It won't give you the answer in decimal because it says this is the exact answer. That's all we can do with it. So put the decimal point in, actually, in this problem. It's hard to say otherwise. On the fancy calculator, make sure it gives you the decimal answer. It will just regurgitate what you put in, right? So I'll put the decimal point here, and on the TI-84, it doesn't matter. It gives you decimal anyway. So I'll push those in, and arc tangent 3/4 tells me 36.869, blah, blah, blah. And so let's round that to 1 decimal place and call that 36 point. Well, this next digit is bigger than or equal to 5. I'll call it 36.9 degrees is the angle there to the nearest 1/10 of a degree. 1 decimal place. So I do that for the first step, and now I've got another angle to find, so I can find the complementary angles theorem and say, let's see, we found alpha here. So beta is 90 minus this. And you can use 90 minus second answer on the calculator. Or if this one I'm rounding to one decimal place anyway, maybe I just want to do it in my head. And I say, well, it looks like 53.1 degrees is the difference there. And I'll just do it in my head maybe. Now, finally, the last step. I can use the Pythagorean theorem to find the last side. This time the last side is my hypotenuse, so it's the root sum square, right? By the Pythagorean theorem, C is the square root of the sum of 3 squared plus 4 squared, which I know, right? My memory maybe is 5, right? This is 9 plus 16 makes 25 squared is 5. Exactly. If I'm rounding this to one decimal point, I could put 5.0. That would be good too. Since it's an exact answer, maybe I'll leave it like that, but if it says round to one decimal place, I'll write 5.0. Look what we found for the famous 3, 4, 5 right triangle you've probably all seen before. The angles you always wondered about are 36.9 degrees and 53.1 degrees, approximately. They're decimals that run on forever again, but these are good approximations. Ever wondered about that? All right. So now you know the angles on 3, 4, 5, right? By the way, I think we started to mention these before, but most right triangles, when you draw them because of the Pythagorean theorem, don't have whole number sides like this. Here's another one that comes up a lot, 5, 12, and 13. I give lots of examples with this triangle so I get whole numbers and it's not so much writing and it's easier to see what's going on. But even though there's an infinite number of these things where the numbers are all whole numbers like this, we call these Pythagorean triples when they're all whole numbers. It's fun. Look on Wikipedia under Pythagorean triples. It'll show you plot the plane where all these Pythagorean triples are. It's very fun to see what they all are. There's an infinite number of them, even not counting the ones that are just gotten by doubling or tripling, all the side lengths. You don't count multiplying all the side lengths. There's still an infinite number of triples of integers, but they're still rare. Most triangles will get decimals like this, right? So it's kind of fun anyway to look that stuff up if you're taking. So just point that out. All right, there's what you do if you have two sides given, right? And then here's another example off of the homework. This is the easiest problem on here, probably. Yeah, here's a triangle. You want to be able to do these in radians also, right? But suppose I say that this is 2 pi over 3. This is 15. This is problem 6b, by the way. Solve this triangle. All right, I'm given an angle on the side. Here's a right angle triangle. So it's a right triangle with an angle on the side given. Maybe I'll call this one alpha, and call this one B then, and this one A, and I've got to find those three numbers. What do I write for this one? Why do I say this one's so easy? This is what we alluded to in the beginning with that picture up there. It's an impossible triangle. I'm like, that one is because you can't draw it that way. But what happens is that this angle here, beta, equals 2 pi over 3. If you figure it, right, that's 2/3 of pi is bigger than 1/2 of pi, right? 2/3 is bigger than 1/2, which is a 90-degree angle, right? So this is bigger than 90 degrees, despite that I didn't draw it that way. These two angles always have to be acute. So that one's a trick problem just to see if they make you waste your time and throw a calculator fit trying to figure out something that's not possible. All right. So there's an interesting one. Well, now comes the applied problems. And I have a strategy for you for this one. My first strategy in applied problems is to always draw a picture. So make a sketch, we'll say. This is so important in these, even though there's no mathematics involved, because it gives you lots of ideas how to proceed. You make this sketch showing all given quantities. the desired quantity or quantities, we'll just say quantity. I like to use quantity, right? That's what Einstein used to say. It makes me sound smarter. Like the desired quantity, put in a letter here as a variable. And then what happens in the picture is often you can see something, right? If you see two sides of a right triangle, you instantly know the third one by the Pythagorean theorem. If you see an angle like this is 35 degrees, you instantly know this angle because they're supplementary, right? So you can see those things once you draw the picture. That's the big advantage here. And so you say, and any consequential measures that you can deduce by supplementary, complementary angles, Pythagorean theorem, etc. There's other ones, problems like this, where you'll see two lines like this, and we'll have this line cutting through, and maybe this is 65 degrees. What's this angle then? It's also 65 degrees. If these are parallel, there's that law for alternate interior angles, saying alternate interior angles are equal. Also, this one is congruent to this one. And because these are supplementary, you know this one, right? You take 180 minus 65 is 115 degrees, and then these are congruent. This is 115 degrees. So you look at all these things you can figure out, and then opposite angles are equal. So this one's equal to this one, and this one's equal to this one, 115. And so some of these things you can fill in a whole lot of stuff once you draw a picture, right? That's what you do. Every time you get one of these applied problems, make a sketch, because it's trigonometry, there's always going to be a sketch. Unlike algebra, where there's not always. But it's showing the given quantities, what you want to get, and anything you can get as an immediate consequence. I think we can get rid of this now. And we'll just write those out as we go now. And so there's a whole bunch of these I'd like you to look at. And by the way, before I forget to say this, next time, let's have another extra credit problem. So extra credit, 3 points again. If you're online, you can do it by email. I'll make it something you do by email. I'll have you do a problem from this section, from the UCO supplement on this section, which is, I think, 5.4. Yeah, 5.4 that we're doing right now. So one of these problems, and I want you to do all of them, 1 through 12, all of them. If you can't do all of them, just bring them to class and we'll work on them at the beginning next time. But one of those problems will be a small extra credit point next time, just for fun. All right. Try and get you caught up, because like I said, this is extraordinarily important material today, even if it's not the hardest material of the course. Here's an example problem. A toy airplane, we'll say a plane, travels bearing, or at a bearing, north 29 degrees west. What is that? Part of the applications are also to get used to common terminology out in, out in the real world. What does that mean, north 29 degrees west? It means if you make this north and west and south and east, from north, you go turn 29 degrees towards the west. So that means that this angle right here, let's not draw it so far, is 29 degrees. Plane travels bearing right over here, north 29 degrees west for 2 hours, I think it was. 2 hours at 9 miles per hour. Right? Turns, makes a right angle turn. Turning right 90 degrees, and then travels 3 hours Pretty good model airplane, right? Travels 5 hours. That's, 15 miles per hour. At the end of all this, what's its bearing from the starting point? It'll be north so many degrees west or east, or south so many degrees west or east. What is its bearing from the starting point? Above that. This one is screaming for a picture, I think. This, right, so here's how it travels. It travels out here, and then it takes a right-hand turn and goes over here somewhere. And then you're asking, so you draw the picture, right? What's its bearing if I draw this side? Hopefully I can draw a straight line. What is this angle here? That's what I want to know. I want to know this angle right here, which we could give it a name. Let's call it theta. What is theta? So what I do is I draw this sketch and I put in what I know, like what's the length of this side? I can figure it out from what's given. Part of this is figuring, not just being given the whole number. Well, the length of this side here is what? It travels 9 miles per hour for 2 hours. So I write it this way, 9 miles divided by hours. This is the other way of writing miles per hour. MPH, miles per hour, in units is miles divided by hours. And then I do this for 2 hours. So I take my rate, 9 miles per hour times my time, gives my distance, right? So this distance is rate times time. The hours canceling gives me miles. 9 times 2 is 18 miles. So I can put that on there, 18 miles. Now, because it makes a right turn, I have a right angle here that I put in. And then over on this side, what do I have? Well, here I'm traveling 15 miles per hour, and I'll use this form of the units, miles divided by hours. That's the rate, and then times time, I'm going 3 hours. I notice since they're the same units hours, I can cancel them, and I got 15 times 3 is 45 miles on this side. So 18 by 45 by who knows what over here. If they said what's the distance, I could use the Pythagorean theorem to find this side of the right triangle, right? No, they asked me to find the angle, of course, right? So what is that angle? Well, what I can do is just look at the picture and figure it out, right? I say, well, from the right triangle picture, I can figure out this angle, right? If I just do this angle, we could call this one alpha. It doesn't matter which angle, alpha or beta. If I just found that, I could subtract 29 and find out what theta is. So that's what I'm going to make my strategy. I want to find this angle given these two sides. There it is. Given two sides, find this angle. I don't have to solve the whole triangle this time. We'll just say, well, let's see what relates this angle to these two sides. Opposite over adjacent or adjacent over opposite. I picked the one that gives tangent rather than cotangent because that's on my calculator. I will say tangent of alpha here is equal to 45 over 18. Now, it actually wouldn't be so bad to say, well, I know these two sides, I'll figure the third side with the Pythagorean theorem, but since you don't need it, I won't bother to do that. Often you'll do that kind of stuff. So I'll say that by a trig relationship, this is opposite over adjacent to the given angle alpha. And now, let's see, alpha then must be in any triangle, the angle's acute, so it's just alpha must be the inverse tangent, right? Anytime you have a trig function equal a number and the angle's acute, you just take, oh, that's the inverse tangent. But and let's see what that comes out to be. Inverse tangent, 45 divided by 18 gives me 68.1985, and if I degrees, if I round that maybe to 69 degrees, maybe it says round to the nearest whole degree. Oops, 68 degrees. This is 5. This is less than 5, so I'll call it 68 degrees. All right. Now, what is theta? So theta is 90 minus that. 90 minus 68 degrees gives me 22 degrees. So now my answer is supposed to be the bearing, though, so I'll call that 22 degrees east of north. So I'll put north 22 degrees east. Bear in mind, when you do these applied problems, there's a lot of stuff. It's easy to make a mistake and wonder, did I get it right? Look on the back. A lot of the answers are in the back, right? It's just the final answer, not the steps. But you can check it that way. And if you can't bring it by class, ask me next time, or come by my office hour. I'm online for all my office hours. Plus, I'm sitting in the classroom, so we can social distance and hopefully not spread anything. All right. Either way, and then if you can't come by my hours, they're tough. Down at the end of the hall on the right, the tutors are now there. They're not real busy right now. Not that many people come in. You can sit far apart in that big room down there. It's computer terminal room. They'll have a tag on that says tutor, and you can figure out who the tutor is and ask them. They tutor classes through calculus, and so you can ask them trigonometry, certainly, right? And they'll help you on your trigonometry. All right. Here's another fun problem. This is number 9. When you try your homework, a 400-foot monument is viewed by someone in the building. Viewed from a window. Put a condensed version of this problem. In a building. Has angle of elevation. That's an angle up from horizontal. So I told you we're learning terminology here. Angle of elevation, like a gun turret. How high up is it from horizontal? Angle of elevation. 18 degrees to the top. And angle of depression, that's down from horizontal. 3 degrees to the base. How far away is it? You're gonna walk to the Great Pyramid of Egypt or something. You want to know how far away it is, and you got your handy dandy sextant out there. Astronomers have it. Measure those angles. You can figure exactly how far you're gonna have to walk, right? With the applied problems, you want to draw a picture, right? So maybe here's the monument. I'll just draw it as a stick figure. Maybe it's an antenna, right? So there it is, and it's very tall, and you're sitting over here in an old tiny building, right? And looking out the window, you consider this angle down to the base and say its angle from horizontal, here's horizontal, is 3 degrees. And then its angle up to the top was 18 degrees. So there it is. How far away is it? You want to write that in too, right? These are the givens, 3 degrees, 18 degrees, and one more. This whole thing is 400 feet tall. So there's all the givens. Then you write in what you want to find, right? I want to find this distance D. So I could call it D, or maybe I should just call it B or something. This is also the base down here. There's a lot of ways you can solve this. But they're all kind of complicated. What can I do with that? So this one enters not just solve a triangle, but you've got to relate the things that are in here. How about that? Well, here's a good idea. Maybe I'll say, let's call this one X. All right. And then this one, if it's, the whole is 400, must be 400 minus X. Let's put this out here. So this one must be 400 less X. And what's more, since this is a horizontal line here, this is a right triangle here and a right triangle here. So there's what I know, all those things. There's some other things I can figure that aren't so useful, like I can say, well, these are two parallel lines, assuming it's horizontal ground. And so this angle is 3 degrees also, and that kind of stuff. But I don't see that that's going to be useful. Instead, I'm going to say this. How can I relate these things? Well, in the big triangle, I can relate the two numbers well, let's say in neither triangle do I have two things known, two independent things, right? I know only one angle here. I could figure the other one that that's not independent. And here I only have one angle. And then I don't have a number over here. So I can't solve either triangle yet. But if I write down the relationship for both of them, I could say, let's see, the tangent of 18 degrees is this over this, right? By trigonometry, the tangent of 18 degrees is 400 minus x over b. All right? And then also in this right triangle, the tangent of 3 degrees is opposite over adjacent, is x over b. So I have those two relationships, right? This is a harder problem, but this is the kind of thing I want you to be able to do still. Well, let's see. I can solve each of these things for b, right? I could do this and say, b times tangent 18 degrees by multiplying both sides by b here is 400 minus x. And the second one multiplying by b gives me b times tangent 3 degrees equals x. All right. And now there's a bunch of algebra ways to proceed. Let's do this. Let's just solve for b in each of them and say in the first one, b is equal to 400 minus x over tangent 18. And in the second one, b is equal to x over tangent 3. I can solve for b in both of them, and now that means I can set these two equal, right? So if I set those two equal, then I get x over tangent. This implies, the arrow means if that is true, then this is true. It means that implies this. That means that the two are equal. X over tangent 3 degrees. Let's see. So I've done it the other way. This will work. Equals 400 minus x over tangent 18 degrees. And I can solve this for x because now I've got it down to one variable. All right, so what can I do with this one? There's a number of ways to proceed again. I could cross multiply since these are equal, and I could say x tangent 18 degrees equals 400 minus x times tangent 3 degrees. I can multiply them out and get x tangent 18 degrees equals 400 tangent 3 degrees minus x tangent 3 degrees, and I can group like terms. So let's add this one over here and get x tangent 18 plus x tangent 3 equals 400 tangent 3. I'm just trying by algebra to group these like terms. I can factor x out of here. X times tangent 18 plus tangent 3 equals 400 tangent 3. And now I can divide by tangent 18 plus tangent 3 and get x. Here's my height up in the building is 400 tangent 3 degrees over tangent 18 plus tangent 3. Let's see what that is, my height in the building then. If be careful on this one. When you do this division, you need to put these in parentheses on your calculator. Be careful with your divide that you divide parentheses. 400 divided by parenthesis, tangent 18, and close your parenthesis here, plus tangent 3, close your parenthesis here. So when you put this on the calculator, make sure you close each of these. If I don't close the parentheses on this one, it will take tangent of this whole thing that's left and give you the wrong number. So close each tangent on this one, or it will get you way off. Let's see what I get. I get 1,060 to the nearest foot. That can't be right. Oh, I forgot my times tangent 3. 400 divided. That's what happens when I try and talk and do it at the same time. Here's the nice thing about having one of these graphing calculators too. It shows you a whole statement. You catch a mistake. On the one line one, it works for this class. You don't get to do that. Look back and see everything you type in. So I forgot to multiply by tangent 3. That should have been 55.6 feet to 1 decimal place. All the units on the side of the triangle will be the same, since the height was in feet before. This will be in feet here. There's x, and now I can find it because over here I have b is equal to x over tangent 3. So then b equals x over tangent 3 degrees. So let's divide this by tangent 3. And I get 1,060 feet. Right. Yeah. So there's there's how far away I am from the monument. About a fifth of a mile, right? All right, so try all those problems and bring some next time, because these applied problems that you can see can be a little complicated in the algebra. All right, and again, 3-point quiz on something similar to one of them. Thank you, everybody online, for coming in too.